Hey guys, so today I sort of wanted to give a little bit of a talk on lambda calculus and digital logic, right? And so you're gonna have to stick with me on this one because it's a bit of a wild one. And by the end of this video, you'll understand that these two are one and the same thing, in that they sort of describe a computational model. And so before I get into any of the math, I kind of wanted to give a bit of context of how things came to be. And so we're going to start in the 1930s. So this is a time period, right, where computers didn't even exist. And so there's this guy called Alonzo Church, right, some genius working at Princeton. He asked himself a pretty interesting question, and it was something along the lines of, what if we could boil computation down to pure functions? What this guy cooks up is straight up just mesmerizing. He comes up with lambda calculus, right? I'll be going over pretty simple rules later on, don't worry. So there's no hardware here. It's kind of just black magic substitution. It's called beta reduction, right? He casually drops this in 1936. Answers a pretty big question at the time, though. Can we decide if math statements are provable? The answer was no. So meanwhile, Church was like scribbling about in functions. The most badass dude ever, in my opinion. You might have heard of him, Claude Shannon. He's over at MIT messing around with wires and switches. So this dude is 21 and basically just casually invents digital circuits in his master's thesis in 1937. So he realized, right, like while playing around with his wires and switches, that they were quite literally perfect for representing Boole's old school logic. You know, that's why it's called Boolean logic. So like and, or, not, true and false, that sort of thing. Maybe you've heard of it, right? Shannon is like, hang on a second. I can wire these babies up to do math. Turn logic into circuits. And voila, we have digital logic. Funnily enough, though, he actually becomes Church's PhD student at MIT in the 40s. The last piece of the puzzle is a guy called Alan Turing all the way across the pond in England. So just about the same time in 1936, Turing comes up with what's known as a Turing machine. So just a tape, a head, and a few rules to shuffle around symbols. So Alan Turing essentially asked the same question that Church did. What can we compute? He essentially proved what's known as the Entscheidung problem, and it was a no-go, right? So this is just a challenge in 1928 by David Hilbert. He's asking for an algorithm to say yes or no to whether a math statement always holds. And you can read up more about that if you'd like. And so Turing and Church would later meet up, right, and discuss their ideas. And they decided, like, hey, you know, you realize more or less that we actually came to the same conclusion just using different methods, right? But it's the same thing, right? These are models of computation. And so it became known as the Church-Turing thesis. Alright, so I think that's enough background information, but it does give you a bit of context as to how this entire thing sort of just unfolded. So let's start off with a basic function in math, right? F of x is equal to x plus 1. This is fairly straightforward. I don't think I have to explain this, but how would you write this in lambda calculus? And so you would do what's called a lambda abstraction, right? And so you can think of this like f of x dot the period symbol here. You can sort of think of it like an equal sign. It's not exactly a perfect analogy, but if it helps you to understand, then fair enough, right? And you've got your function definition over here, or your expression. Nothing too difficult, I don't think. Now let's look at how we would evaluate a function normally. So f of 2 is equal to 2 plus 1. You just do some simple substitution. You get 3, right? Nothing fancy going on here as yet. Now, in lambda calculus, it's called beta reduction, okay? What you do is you introduce this sort of strange notation here, or with brackets at the side. And so you indicate, right, that you're substituting 2 for x. And so you would get 2 plus 1 is equal to 3. Hopefully all of this is simple so far to follow along. Now in general, if you had lambda x dot m, m denoting some expression, it could be x plus 1, could be anything. It can even be another function, as you'll see later on. And n being some parameter, you can write this as m, square brackets, n slash x, meaning replace all x in m with n. Or if you'd like to think of this in a slightly different way, but same thing really. You have some expression m, right? And you're substituting n, right, where x is supposed to be, or where x currently is. Okay, so you bring in n and you shift out x, if you want to think of it that way. And so I know it can seem a little bit daunting, it's like fancy notation, but the ideas are quite simple really. Now let's talk about something called church encodings. And so, okay, this talk is about digital logic and Lambda calculus, okay? And so we need the foundation for digital logic. So we need true and false, right? We need Boolean algebra. And so the way you represent that is with church encodings for true and false. And so let's take a look at true. So we've got lambda x dot lambda y dot x. Okay, this probably looks like gibberish to you right now, but remember we said that we have some lambda abstraction here, lambda x, and everything that comes after the period is the expression or the function definition. And so this is a function, right, which is defined in terms of another function, okay? And so I think an example, yeah, will help to clarify this, but just to tell you straight off the bat that the true is going to take in two inputs, x and y, and return the first input, x. False is going to do the same thing, take in x and y, however, it's going to return the second input, y, instead of the first one. So let's take an example on beta reduction for false, and so hopefully this is going to help. And so we have lambda x and lambda y. This means that we need to supply two parameters. And the way this is done is that you beta reduce one parameter at a time. And so the first parameter is going to be this 1 that we're going to bring in, right? So n in this case is 1. Remember, in general, when we're beta reducing, we just went over this, right? And so everything that comes after the period for this lambda abstraction is what's known as m. Okay, and so that's in general, right? And so what we're doing is we're going to substitute n in place of x. But if you pay close attention here, right, there's no x, and so nothing happens, right? Then we supply the second parameter, which is 0, and this is applied to this lambda abstraction here, and you can see then that m in this case is y, and so we substitute n in place of y, and so what happens then is 0 is going to come here, and so our function is just going to pick 0 as our output, right? And so you can see what false quite literally did was it took two inputs and it returned the second one. You can feel free to go ahead and do the beta reduction for true, and you'll see that it's going to take two inputs and select the first one instead of the second. So let's talk about the NOT gate. So this is pretty straightforward, and if you can start to understand what's going on here, I think you've got a pretty strong grasp already. So we've got lambda a dot a, false and true, and these two are going to behave like parameters you're going to see in just a minute. And so the false and the true is quite literally what we just discussed as the church encoding. Let's take a look at this. We're going to do beta reduction on NOT, and so you can see then that we've expanded this out, or we substituted in false and we substituted in true, right? And so what's going to happen, right, when we beta reduce is this true is going to come in here and replace, and so it should already start to become a bit clearer to you what's going on. And so we end up with true, false, true. And you'll see then that false is selected via the definition of true. Now you might be wondering, okay, what's going on here, right? And so in lambda calculus, your leftmost statement is really one of the most important ones, right? You can see here, by the definition of true, it's expecting two inputs, x and y, and it's going to return the first input. And so the inputs are already here, right? So this is going to serve as an input here, and this is going to serve as an input into this lambda abstraction as well. Okay, and so these expressions are not being computed. Well, they are being computed, but just not as separate lambda abstractions then. You sort of think of it as a beta reduction, right? Where this here is what we're reducing. Okay, and if you remember from the definition of true, what is it going to do in this case? If we give it true, it's going to return the first input, which is false, all right? And that's quite literally what NOT is supposed to do, right? You give it true, it's supposed to spit out false. And if we gave it false, right, it's going to select what? The second input from the two parameters. And so the second input in this case would be true, right? And so if we gave it false, it would return true. Precisely what we need a NOT gate to do. And so we've got our NOT gates. Let's talk about the AND gate. Now, AND gate is taking in two inputs, lambda a, lambda b, right? And the expression, right, or the function is defined as a, b, and f, okay? Now, I didn't particularly see it necessary to do a beta reduction example here, because conceptually I think you should already see what's happening, but let's sort of like in our minds go over what would happen here, right? If we gave, for instance, true and false, right? So if true and false were our inputs, right, we would have true, false, and false, right? Okay, now remember, as we said, the leftmost input is the most important one, and these two would be the parameters into A, right? And so we've got true, false, and false. What is going to happen? Can you predict? A, since it's true, right, is going to take the first input. It's going to take B, and so it's just going to evaluate to false. And anytime A is 0, right, it's just going to pick the second out of the parameters, so it's going to pick up false every single time. And so you can kind of see what's happening here. And then if A is 1 and B is 1, then A is going to just select the first input, which is B, so it's going to come back as true. And you can double check with your true table at the bottom here that it holds for all the other cases. And feel free to just handwrite the beta reduction. I think going into the gory details often is quite helpful. And so the OR gate is also quite simple. We're taking in two inputs, A and B, right? And the expression is simply A, true, and B. And so suppose that we supplied 0 and 0 here, right? Or false and false. Okay, and this would beta reduce to false, true, and false. And again, false would select the second output, so it would just be false, right? And if this was just true, right, and if B was false, then this would select the first input, which is true. And in the event that A was false, right, and B was true, then it would select B as being true. So it functions exactly as you would expect an OR gate to function. And so we've got true and false, we've got not, we've got and we've got the OR gate. And so what we have, right, this set is functionally complete. We can construct any truth table, right? And so what this proves then is that Lambda calculus really is just a model of computation, right? So anything you can build with a circuit or with digital logic, you can represent with Lambda calculus. Anything you can compute. And so let's just try to generalize this now. And so I won't be going over what sum of products is. I sort of already covered this in my Introduction to Digital Logic 1, and we did cover the half adder as well. And so the sum of products expression from the truth table would be A and not B, or not A and B, right? And so the way you would go about writing this in Lambda calculus would be, think about it carefully, right? We're getting two inputs, right? So lambda A dot lambda B, that wasn't too hard to figure out. Now this is the kicker here, and I think once you see this, if you know a bit of digital logic, then everything you know will just transfer straight over into Lambda calculus. And when I was first starting out with digital logic as well, I found this to be quite helpful, and it's called retrograde analysis. It's also a very powerful technique if you're playing chess, for instance, right? You think about the end state and you work backwards towards the starting position that could potentially get you there. Okay, so you think about potential end states and you work from the end state back to where you are now. It's a very, very powerful technique. So you kind of do the same thing here, right? You think about the end state. If you were to imagine or envision what this circuit would look like, at the very end, right, we would have an OR gate taking in two inputs. And so this is our most important expression, right? And so this comes here outside, OR. And we already have a definition for OR. And so our OR is going to be taking in some two inputs, right? We don't know as yet. Well, we know here, but exactly what are those? Well, it would be, you do the same thing again, right? And so, but there's not many layers of abstraction here, so it's quite simple. You can quite literally see that inside of here we just need an AND gate, right? So we would say AND. We already have an expression for AND. AND takes in two parameters, A. However, it takes in not B, and recall that not B in and of itself is a lambda abstraction, and so when you're beta reducing, right, it would, B would be flipped. It would invert B, and then it would beta reduce that output into the AND lambda abstraction, and so it would continue onwards. And so it's sort of like unraveling itself as it goes. And then, okay, we've got the other parameter over here, much the same thing, and B. I just switched the ordering around, it doesn't matter, and B, not A. And so there it is, right? It's quite simple, but it's really, really powerful. And so this really just goes to show you that having some very, very simple rules can produce extreme amounts of complexity, right? Like it doesn't seem intuitive at first, but you know, it's right in front of you here. And this kind of reminds me as well of something I came across many, many years ago. It's called Conway's Game of Life, right? And there's this video somewhere on YouTube, I think it was called Life in Life or something. I can't quite recall if that was the title of the video, but it was showing then that you can create logic gates inside of John Conway's game of life, right? And if you can create logic gates, well, obviously you can represent any kind of computation. And so what they did was that you have a simulation that's running a simulation, that's running a simulation, that's running a sim. It just goes on and on. It's like a fractal pattern, right? It just goes on forever. And so it's really quite interesting. And I think this sort of relates to this notion of computational irreducibility as well. If you're interested in that sort of thing, you can listen to a couple of talks from Stephen Wolfram, for instance. But okay, I think that's really all I wanted to show you. And so if you know, right, some digital logic, then functional programming becomes quite simple from here on out, because all of the functional programming, for example, like Haskell, right, is built on top of Lambda calculus. So if you can do this, then it automatically translates, right? And so it's very important that you understand what the foundation is, and then you go from there. And everything else just sort of stems from these very simple rules or axioms, right? You sort of build an entirely complex system. But alright, I hope you learned something, and if you have any questions, feel free to ask. I'll do my best to answer.